Hello everyone, welcome back. Now let's solve another important exam problem using Gauss's law. If we look at the figure, we have a thick spherical shell with a uniform volume charge density. The inner radius is 10 centimeters, the outer radius is 20 centimeters, and we are asked to calculate the electric field at 6 different locations. A, R equals 0, B, R equals A over 2, C, R equals A, D, R equals 1.50A, E, R equals B, and F, R equals 3.00B. Before we begin, let's do a quick review. For spherical symmetry, we use E equals K times Q enclosed divided by R squared. The enclosed charge is rho times the enclosed volume, where rho is the volume charge density and V is the charged volume inside the Gaussian surface. The most important idea is that the electric field depends only on the enclosed charge, not on the total charge. Now let's solve the problem step by step. Step 1. Cases A, B, and C. For case A, R equals 0, case B, R equals A over 2, and case C, R equals A, the Gaussian surface encloses no charged material. Therefore, the enclosed charge is 0, and the electric field is also 0 at all 3 points. Step 2, case D. Now consider case D, where R equals 1.50A. This Gaussian surface passes through the charged shell, so only part of the shell is enclosed. First, calculate the enclosed volume using 4/3 pi times, open parentheses, R cubed minus A cubed, close parentheses. Next, multiply the volume by rho to obtain the enclosed charge. Finally, substitute this enclosed charge into E equals K times Q enclosed divided by R squared. The electric field is approximately 7.31 newtons per coulomb. Step 3, case E. Now consider case E, where R equals B. At this position, the Gaussian surface encloses the entire charged shell. Calculate the total shell volume, then the total charge, and substitute it into Gauss's law. The result is approximately 12.1 newtons per coulomb. Step 4, case F. Finally, consider case F, where R equals 3.00B. This point is completely outside the shell. The enclosed charge remains exactly the same as in the previous step. Only the distance increases, so the electric field decreases according to the inverse square law. The final answer is approximately 1.35 newtons per coulomb. Excellent work. This problem shows that in every Gauss's law question, the first step is always to determine the enclosed charge inside the Gaussian surface. Now let's move on to the next important exam problem. Now let's solve another important exam problem on Gauss's law. If we look at the figure, we have a non-conducting spherical shell with an inner radius of 2 centimeters and an outer radius of 2.4 centimeters. Its volume charge density is A divided by R, where A is an unknown constant and R is the distance from the center. Also, a positive point charge of 45.0 femtocoulombs is placed at the center of the shell. Remember that 1 femtocoulomb equals 10 to the power of negative 15 coulombs. We need to determine the value of A so that the electric field remains constant everywhere inside the shell. Before we begin, let's do a quick review. We will use Gauss's law, E equals 1 over 4 pi epsilon 0 multiplied by Q enclosed divided by R squared. Since the charge density is not constant, we also remember that dq equals rho times dv. And for spherical symmetry, dv equals 4 pi r squared dr. The key idea is simple. For the electric field to be constant, the final expression must not depend on r. Now let's solve the problem step by step. Step 1. Calculate the enclosed charge. This problem is slightly different from the previous one. In the previous example, the charge density was constant, so we simply used Q equals rho times V. However, in this problem, the charge density is A divided by R, which changes with the distance from the center. Because the charge density is variable, we must use integration to calculate the enclosed charge. For the shell region between A and R, we write Q shell equals the integral from A to R of rho dV. Now substitute rho equals A divided by R prime and dV equals 4 pi R prime squared dr prime. After simplifying and integrating, we obtain Q shell equals 2 pi A times open parentheses R squared minus A squared close parentheses. Finally, we add the point charge at the center. So the total enclosed charge becomes Q enclosed equals Q plus 2 pi A R squared minus 2 pi A squared. Step 2. Apply Gauss's law. Now substitute the enclosed charge into Gauss's law. After rearranging the equation, the electric field becomes the sum of two terms. The first term contains 1 over r squared, while the second term is simply A divided by 2 epsilon 0. Step 3. Make the electric field constant. Since a constant electric field cannot depend on r, the coefficient of the 1 over r squared term must be 0. Therefore, we write Q minus 2 pi A squared equals 0. Solving for A gives A equals Q divided by 2 pi A squared. Finally, substitute the numerical values. The answer is 1.79 times 10 to the power of negative 11 coulombs per square meter. Excellent work. This problem demonstrates an important idea in Gauss's law. Whenever the charge density varies with position, we calculate the enclosed charge using integration instead of the simple relation Q equals rho times V. Let's summarize the most important ideas from Gauss's law. First, electric flux. Electric flux represents the number of electric field lines passing through a surface. Its mathematical expression is phi equals the surface integral of E dot dA. Next comes the main result of this chapter, Gauss's law. It states that the total electric flux through any closed surface equals the enclosed charge divided by epsilon naught. One very important point to remember is that the size and shape of the Gaussian surface do not matter. Only the charge enclosed inside the surface determines the result. Now let's review the three most common symmetry cases. For a point charge or a uniformly charged sphere, we choose a spherical Gaussian surface. The electric field is E equals KQ divided by R squared. For an infinitely long line charge, we choose a cylindrical Gaussian surface. The electric field becomes E equals lambda divided by 2 pi epsilon naught R. For an infinite plane sheet of charge, we use a pillbox Gaussian surface. The electric field is E equals sigma divided by 2 epsilon naught. Finally, remember the 5 problem-solving steps. Identify the symmetry. Choose the correct Gaussian surface. Find the enclosed charge. Apply Gauss's law. Then solve for the electric field. Excellent work. You have now completed the entire chapter on Gauss's law and solved many important exam-style problems. I sincerely hope these lessons help you understand the concepts more deeply and perform better in your exams. If you enjoyed this course and found it useful, please support the channel by liking the video, subscribing, and sharing it with your classmates. Your support helps us continue creating high-quality engineering courses. The next chapters will be produced with your continued support, and I can't wait to see you in the next chapter of Physics 2. Thank you for watching, and see you in the next lesson.